of porosity, moisture content, and field capacity. So imagine we have some volume of, say, a soil or a rock, doesn't really matter, that's enclosed by this white line. And the total volume enclosed here is referred to as V sub T, total volume. Now I'm going to imagine putting into that volume some amount of solids, say some sand grains or some silt grains. So those are the little gray things here. So the volume of these solids here I can just call V sub S, volume of solids. And the air, the empty space, not the solids, is referred to the volume of the voids. So the volume of the solids plus the volume of the voids, that will equal the total volume. Now, the porosity N is defined as the volume of the voids divided by the total volume. So it represents the fraction or percentage of the total volume that is just empty space. Typically in rocks and soils and geologic materials, porosity will range from near zero in some materials, some rocks, to maybe about 50% or 0.50. In soils, this is all materials. In soils, the lower range is actually more like 0.20 or 20%. So porosity in soils ranges from about 20 to 50%. This is to say that between 20 and 50% of the soil consists of just basically dead space that can be filled with anything. Now, if I now start putting something in there, if I put some water into that empty space here we go. I put some water into that pore space now. I'm going to define here the volume of the water as VW. So the pore now, the pore space, the void space, consists partly of water and partly still of air. The moisture content, theta, is defined as the volume of the water divided by the total volume of just the water. And notice that theta, therefore, can never, will be in some cases, in most cases, less than the porosity like it is in here, but it can never exceed the porosity. When the pore space is entirely full of water, then the moisture content is equal to the porosity. When it's got some air in the pores in addition to water, then the moisture content will be less than the porosity. We call this state, where some of the pores have water and some of the pores still have air, as the unsaturated zone. Unsaturated zone, meaning that the pore space is not saturated with water. Some of the pores still contain air. And this is generally found close to the surface, where the pore space will have both water and air. If we fill all the pores with water, like this case here now, so this again is the volume of the water, now the moisture content is equal to the volume. It's always equal to the volume of water divided by the total volume, but now the moisture content is also equal to the porosity because the pores are completely full of water. And so this is the case that we generally see below the water table, deeper down into the earth, and we call this the saturated zone. Saturated zone. So in general, the saturated zone is found deeper into the ground, and the unsaturated zone, where there's air in the pores in addition to water, is closer to the surface. Finally, if we grab a sample of this soil that's saturated with water and allow it to drain, just drain naturally under the influence of gravity. So just let this water sort of seep out of this thing, we will find that not all of the water will drain from my sample. And the reason is that some of the water is retained in the sample through attraction between the water molecules and the solids, a phenomenon we call surface tension. So the surface tension retains some of the water in the sample. And if we allow this thing to drain just under the influence of gravity for about a day and a half, 30 hours or so, we achieve a moisture content that looks like this, and this is defined as the field capacity moisture content. So it represents the moisture content of the sample after a saturated sample has been allowed to drain under the influence of gravity. And you can see that it's less than the porosity, but it's not zero, right? Some water is retained in the pores at the field capacity.